When you watch an electric vehicle's quiet glide down a highway, or hear the steady thrust of a commercial jet engine, it is easy to assume you are looking at triumphs of pure modern engineering. Yet none of these modern machines function without a material originally named after a mischievous goblin from ancient folklore. This is cobalt, element 27. It is a hard, lustrous, bluish-gray transition metal pulled directly from the earth. Long before anyone conceived of smartphones or electric cars, human beings prized this unique chemistry for a singular aesthetic purpose. When mixed into glass and ceramics, cobalt compounds yield incredibly intense, striking shades of blue. The extraction of this color came with strange hazards. Early German miners noticed that certain mysterious ores failed to produce copper or silver, and instead released dangerous, sometimes lethal fumes when smelted. They blamed these yields on the cobalt, a malicious spirit believed to live in the rock. The superstition persisted until the 18th century, when Swedish chemist Georg Brandt isolated the material. He proved the toxic fumes and the vibrant blue colors weren't the work of spirits, but a distinct chemical element. The mysterious rock had an identity. It sat largely dormant in the earth, possessing unique physical properties that waited for the high heat and high energy demands of the industrial age. That changed in the 20th century. As industrial and military ambitions grew, engineers hit a wall. They needed to build machines that operated in environments hot enough to warp, melt, or shatter traditional metals. The solution was the superalloy. By mixing cobalt into existing metal alloys, engineers found they could create a new material capable of retaining its mechanical strength and structural integrity under immense thermal stress. You see the direct application of this chemistry inside the high-temperature environments of modern aerospace engineering. As internal turbine blades spin thousands of times per minute, absorbing explosive exhaust heat, cobalt mixed into the metal prevents the rapidly moving components from deforming mid-flight. The identical chemical element that ancient artisans used to tint fragile blue glass had become the unyielding thermal armor required to build humanity's most aggressive machines. While cobalt conquered the sky, a different engineering challenge emerged on the ground. The late 20th century required energy storage that was compact, portable, and reliable. In the 1990s, the push for portable communication forced a rethink of hardware design. Lithium-ion batteries arrived to untether electronics from the wall socket, allowing laptops and phones to function far from a permanent power source. To make this battery chemistry work, cobalt is placed in the cathode, the positive side of the cell. Here, the cobalt atoms organize into a rigid lattice structure, acting as a chemical scaffolding. This scaffolding is crucial. It holds the highly reactive lithium ions securely. Because the cobalt framework remains perfectly stable during charging and discharging, the battery achieves a high energy density without breaking down, degrading rapidly, or catching fire. That thermal and chemical stability allowed engineers to scale the technology upward. The chemistry that energized a pocket-sized handset was now capable of propelling a multi-ton vehicle across a highway. Through its role in the cathode, element 27 transitioned from a specialized industrial alloy into a foundational component of the global electrification movement. However, the sudden demand required to hit green energy targets exposed a severe geographic bottleneck in the supply chain. This map visualization outlines the geographic reality of cobalt extraction. A vast majority of the world's historical and current supply is hyper-concentrated in a single region, the Democratic Republic of the Congo. The extraction of these resources carries severe consequences. Alongside enormous environmental damage, the rapid scaling of mining operations has raised documented human rights concerns, particularly regarding the high risk of child labor and dangerous working conditions in parts of the country's artisanal mining sector. This creates a direct paradox. Global industries require these batteries to shift away from fossil fuels and build cleaner transportation, but securing the materials for that future exacts a heavy toll on vulnerable communities right now. In response, industries are scrambling to adapt. Current efforts are heavily focused on establishing strict supply chain transparency and responsible sourcing audits to ensure worker protections at the extraction level. Engineers are also building out a circular economy. Advanced recycling facilities are now capable of shredding spent batteries and recovering the valuable cobalt within them, reducing the total volume of raw ore that needs to be mined. Simultaneously, material scientists are working to engineer entirely new battery chemistries that use a fraction of the cobalt or remove it from the cathode entirely. Cobalt is currently caught between the technology that sustains our modern lives and the sustainable world we are attempting to build. It has traveled from ancient pigments to aerospace superalloys to the center of the electric age. The element itself hasn't changed. The only remaining question is how we choose to use it.